Section 8.4 talks about perfect numbers. So this is just a little example topic, but we'll see at the end that we'll be able to do a set equality proof related to these perfect numbers. So it sort of ties into what we're seeing, but it's an interesting sort of type of number. It's an interesting definition, and it gives us sort of an opportunity to learn cool facts about math. So the first question is, what is a perfect number? So a number is perfect if it's equal to the sum of its positive divisors less than itself. So let's unpack that. So maybe I can start with a number here, like 4, and I can write out the divisors of 4. So 1 divides 4, 2 divides 4, and 4 divides 4, but I only want to think of the divisors that are less than the actual number, and then I can add up those divisors, and I get 3. So 4 is not equal to the sum of its positive divisors, so 4 is not perfect. Now if I do the same thing with 6, the divisors of 6 are 1 and 2 and 3 and then 6. I'm only thinking about the ones less than 6. I add those up and I do get 6 here, so 6 is perfect. So we want to think about the numbers that satisfy this. So I encourage you to take a little second and see if you can find other perfect numbers. And here we found that 4 wasn't perfect. The sum of its divisors was less than 4. Are there other numbers where the sum of the divisors is greater than that number itself? So go ahead and see if you can investigate that a little bit. All right, so here are some perfect numbers. 6, which we already talked about, 28, 496, 8,128, 33,550,336. Right there, got quite big, quite fast. And in fact, these are the first 5 perfect numbers. So there's no number between 6 and 28, which is perfect. No number between 28 and 496. No number between 496 and 8,000. And the next one after 8,000 is 33 million. So there's not very many, for some definition of many, perfect numbers. So I encourage you to look at these numbers that we have and see if you notice any patterns that they satisfy. See if you can kind of come up with any conjectures about these perfect numbers. Okay, so I wrote down several conjectures that I noticed. One of the things I noticed about the 5 numbers that we had was that they're even. They all were even. In fact, they all ended in either 6 or 8. And we also found that there weren't very many perfect numbers. So I would have to say, what do I mean by aren't very many? Right? So maybe there's only finitely many. That would be one way of saying there's not very many. There's only 15 of them. Or there could be infinitely many. We could talk about maybe their density, so how many there is in a specific range. And that would be another way, even if there's infinitely many, if they're not very common, then we could still say there's not very many if there's infinitely many. So I encourage you to kind of think about that. So go ahead, come up with some more conjectures, and we'll talk about those in class. But let's actually talk about the truth values of these. Perfect numbers are even, right? No one knows. So far, no one has found an odd perfect number, but they have also not been able to prove whether or not they are all even. And so we also can't say whether or not they end in 6 or 8, because if there is an odd one, it's not going to end in a 6 or an 8. But we can say if we have an even perfect number, then it ends in 6 or 8. And I encourage you to think about how you could prove that and see if you can kind of come up with a proof. And then the last fact we have here is that there aren't many perfect numbers. And if we interpret that to mean that there's only finitely many, again, this is actually unknown. People don't know if there's infinitely many or finitely many perfect numbers. So there's a lot of things we don't know about perfect numbers, but we will see that there is some facts that we do know, and that's what we're going to talk about in the rest of this. So Euclid actually looked at these perfect numbers, and he probably didn't say exactly this, but he thought something like this, which is that perfect numbers are related to numbers of the form 2 to the n minus 1 times 2 to the n minus 1. So up here, the n minus 1 is all up in the exponent. Here, I just have that 2 to the n in the exponent, and then I'm subtracting 1 after that, where n is a natural number, and this quantity, 2 to the n minus 1, is prime. So let's see what we mean by is related to. So I want to look at these numbers of this form, 2 to the n minus 1 times 2 to the n minus 1. So I went ahead and I looked at for the first 13 values of n, what numbers we get when we plug them into this. I filled most of it out for us, but I left a little bit for us as an exercise. So when n is 2, I get 2 to the 2 minus 1. So that's 2 to the 1, which is 2. When n is 3, I get 2 to the 3 minus 1, 2 to the 2, which is 4. Then I've got the rest of them for us. When n is 2, I get 2 to the 2 minus 1. So I already found 2 to 2 down here, so I just need to subtract 1. And then same thing here, I subtract 1. Okay, and now I want to think about multiplying these two numbers together when the second one is prime. So the 1 is not prime, so I'm not going to bother with that multiplication. 2 times 3, that's 6. And 3 is prime, so that's why I did that one. 7 is also prime, so I can go ahead and multiply that by 4. 28. 15 is not prime, so I'm going to skip that one. 31 is prime, so I multiply that by 16 to get 496. 63 is not prime, it's divisible by 3. In fact, every other one of these, the alternating ones, are divisible by 3, so those aren't prime. Turns out 127 is prime, so that times 64 gives us 8,128. 511 is not prime, neither is 2047, but 8,191 is prime, and when I multiply that by 4,096, I get 33,550,336. So what we should notice here is that in the case where 2 to the n minus 1 was prime, I got exactly all of those perfect numbers that we were talking about. So now we can state Euclid's conjecture a bit more, which is that perfect numbers have the form 2 to the n minus 1 times 2 to the n minus 1, where that second thing, 2 to the n minus 1, is prime. So let's see what that looks like. So we can consider the statements, or the sets A, where A is the numbers of the form 2 to the n minus 1 times 2 to the n minus 1, where n is a natural number and 2 to the n is prime. And the set P, where P is just a set of perfect numbers. And we can ask ourselves, is it true that the set of perfect numbers is the set equal to the set A? Well, we already said that we're not sure if there are odd perfect numbers. We don't know. And so let's think about if the numbers in A are even or odd. Well, if I think about this, right, when n equals 1, 2 to the n minus 1 is not prime because it's equal to 1. Thus, if something is in A, it's equal to 2 to the n minus 1 times 2 to the n minus 1, where n is greater than 1. Thus, it's 2 to some number greater than 0 times 2 to the n minus 1. So it has that positive power of 2. Thus, A is even. So this is sort of a weird roundabout proof The fact that I already told you there are no odd perfect numbers probably means that you can conclude that this equality isn't true. Because if it was true, since everything in A is even, I would know that every perfect number would have to be even. But since I don't know whether this is true, it must be impossible to prove this as well. So that's not quite true, but it turns out if we restrict ourselves to only looking for even perfect numbers, if we give up on determining whether or not there's odd ones, we can show that all of the even perfect numbers have this form that we've talked about. So let's go ahead and look at that in the next slide. All right, so again, I'm going to have this basically the same sets here. So my A is just this 2 to the n minus 1 times 2 to the n minus 1, where that 2 to the n minus 1 is prime. They sound a lot alike when I say them out loud, but make sure you know the difference between those two quantities. And now I'm updating P slightly. So not only is each of those numbers perfect, they're also even. Then it is actually true that A does equal P. Now the proof is pretty complicated, but I think it's a good example of sort of what these proofs might look like. So we are going to go through and do that. For this proof, we actually need a lemma that you might have seen in Calc 2. Hopefully you did see in Calc 2. So I'm just going to go ahead and restate that here. So it's telling us how to add up a geometric sum. So if I have a geometric sum, so the sum from k equals 0 to n of r to the k, that's r to the n plus 1 minus 1 over r minus 1. Or, in particular, when r is 2, that's the case that we'll need it for, the sum from k equals 0 to n of 2 to the k is equal to 2 to the n plus 1 minus 1. So we'll use this lemma as part of our proof. So I encourage you to refer back to your Calc 2 notes to see why that's true. So the first thing I want to do as part of my proof here is to show that A is a subset of P. So I want to show that every number of this form is an even perfect number. So we can start by assuming we have some number of that form. So we could say x is in A, but then by definition, that means that x is equal to 2 to the n minus 1 times 2 to the n minus 1, where n is in n and 2 to the n minus 1. Oops, 1 should be downstairs. Minus 1 is prime. Okay, so assume I have a number of this form, and I want to show here that x is even and perfect. So we already showed that x is even, right? So since, as we showed, n equals 1, so since maybe we have to put an extra word in there, when n equals 1, 2 to the n minus 1 is not prime. We know n is greater than 1, so x is equal to 2 times, I'm just going to pull out an extra 2 there, 2 to the n minus 2, where this is greater than 0, times 2 to the n minus 1. Right, basically, I'm just saying I have at least one factor of 2 left, so x is even, which is what we wanted to show. Now I need to show it's perfect. That's going to be sort of the meat of this argument. So how can we do that? I need to think about the divisors of x. So I'm going to sort of leave my formal proof writing and I'm just going to kind of show what this is going to look like. If I have a number, right, so let's say we do an example here. We just look at something like 36. I know that that's equal to 9 times 4. So I can drop down to its prime factorization, 2 squared times 3 squared. If I want to try to find the divisors of this, I have to have some number of 2's and some number of 3's. So I can either have no 2's 1, 2, or 1, 3. Sorry, 1, 2, or 2 2s. And then I can have no 3s, 1, 3, or 2 3s. So if I have no 2s and no 3s, then I just get 1. Or I can have a single 2 or 2 2s. And then each of those can go along with having a 3. So I multiply them each by 3. And then we could have a second 3, so I can multiply by another 3. And that's going to give me all of the divisors of 36. All right, so if I add all these numbers up, I definitely get bigger than 36. So 36 is certainly not a perfect number. Right, but this sort of just shows us how we can go about systematically finding all of the divisors of a number if I know its factorization or its prime factorization. Now I know that x is equal to 2, which is prime, to the n minus 1, times 2 to the n minus 1, where this is prime. So I've actually already written x as its prime factorization. So if I think about finding its divisors, I can either have, let's do the 2's across the top, no 2's. All right, so maybe I can think of this as 2 to the 0, or I can have 2 to the 1, or 2 to the 2, all the way up to 2 to the n minus 1. And then going down here, I can either have no 2 to the n minus 1's, or just one of those 2 to the n minus 1's. But I can't break that down anymore because it's prime. So let's think about what this is going to look like. So here I'll have 1, here I'll have 2, here I'll have 4, dot, 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 up to that 2 to the n minus 1. And here I'll have 1 times 2 to the n minus 1, 2 times 2 to the n minus 1, all the way down to 2 to the n minus 1 times, oops, this is, well, I just write the other one, these times each other. Now when I'm considering perfect numbers, I only want to consider the divisors less than the number. So I'm not going to consider that last guy, but I am going to consider everything else. So let's go ahead and add all these up. So if I add the top row, I get 1 plus 2 plus 4, all the way up to 2 to the n minus 1. So that's first term minus first omitted term over 1 minus my common ratio. Or again, we can use this formula up here. I'm just remembering how I like to think about it. So that just gives me 2 to the n minus 1 when I add those up. And then the second one, I can factor out that 2 to the n minus 1. Sorry, minus 1. Do a better job here of writing the appropriate term. They all have this 2 to the n minus 1. Oh man. Well, the last one will have that as well in common. So I have that 2 to the n minus 1 times by 1 plus 2 plus, this one ends 1 less, so I'm only going to go up to 2 to the n minus 2. So that is going to be 2 to the n minus 1 times 2 to the n minus 1 minus 1. And now we have to add these two quantities together. So I'm going to go ahead and expand this out, FOIL that out. Is that what I want to do? I'm trying to show that it's equal to this quantity because I want to show the divisors equals x. So I want to try to find a 2 to the n minus 1 term in both of them. So then that sum is equal to 2 to the n minus 1 plus 2 to the n minus 1 times 2 to the n minus 1 minus 1, which, if I factor out that 2 to the n minus 1 from both terms, the first one I'm left with a 1, and the second one I'm left with a 2 to the n minus 1 minus 1. So those cancel, and I really do get that I get 2 to the n minus 1 times that 2 to the n minus 1, which was equal to x. So it really was true that the sum of the divisors of x was equal to x. So we can conclude that x is perfect. So I definitely encourage you to read through this one more time. You can also read through it in the book. It's Theorem 8.1 in the book to see if you can get a good feel for how this proof works. Now, to finish this proof, we need to show that every perfect number is in that set A. So if it's perfect and even, then it has to be in A. So of that form, 2 to the n minus 1 times 2 to the n minus 1. And this is what we'll show in class. So if you want a head start on that, go ahead and look at the proof. We'll start with any questions you have on that previous proof, and then we'll go ahead and work through this one together in class.